Hey Algebra 1, in this video I'm going to show you the introduction to exponential growth and decay. So before we start the new lesson, let's review real quick. So the two functions at the top, you should already know. The first one is the linear function, and you know that the linear parent function is y equals x, and you know that the graph looks like this. So that's the linear parent function. And of course, you know these different forms, y equals mx plus b, that is the slope intercept. You should also know y minus y1 equals m times the quantity x minus x1. That is point slope form. And of course, the last one is ax plus by equals c. That right there is standard form. So if you were to graph any of these, you should know that they make a line. That's why it's called the linear parent function. Now the second one is quadratic. So the quadratic parent function is y equals x squared. And you should know that the graph is a parabola crossing the origin, which is concave up. So remember, the U-shaped graph is called a parabola. You should also remember y equals ax squared plus bx plus c. That is standard form for a parabola. So both of these will give you a U-shaped graph, a parabola. So both of those are review. So the new one is called exponential growth or decay. So an exponential function. So the equation is y equals a times b to the power of x. And sometimes you'll see it in parentheses like this. So y equals a times b to the x. So you can have two different variations of this. So you can have exponential growth. And if you read the graph from left to right, notice that it is going up. Therefore, this is called exponential growth. The other one is exponential decay. That's whenever the graph goes down when you look at it from left to right. So again, if you start from the left side and if you look at the graph, you can see that it is decreasing. In other words, going down. So this is exponential decay. The graph is going down. So this is the equation for exponential growth or decay. So let's break these variables down real quick. So the very first thing, the A is your initial amount. And you should know from previous lessons, the initial amount always yields the y-intercept. So wherever the graph crosses the y-axis. The B will represent our growth or decay factor. Now, it'll be growth if the B value is greater than 1. It'll be decay if the B value is less than 1. So let's go into further detail about this right here. So it'll be growth if the B value is greater than 1, and you get that from doing the following. You take the 1 and you add the rate. So the rate at which the problem is increasing. So of course, if you do 1 plus a decimal, you're going to get a number bigger than 1. And it'll be decay if you do 1 minus the rate expressed as a decimal. And of course, when you do 1 minus a decimal, you're going to get something less than 1. So in review, if the B value is greater than 1, it is growth. If the B value is less than 1, it is decay. The X and the Y. So we'll talk about this more in our next video, but the X, just know that it represents time. And the Y will represent the total amount. That's more for word problems. But for today, the main thing that you should guys know is that the A represents the Y-intercept. And the B is your growth or decay factor. If it's bigger than 1 is growth, less than 1 is decay. So let's look at two examples. So for the first example, let's look at growth. So let's look at this equation. Y equals 1 times 2 to the power of x. So let's analyze this real quick. Just by looking at the equation, you should know the y-intercept and if this problem represents growth or decay. So the very first thing, our A value is 1. In other words, the y-intercept is 1. The B, which in this case is a growth factor, it is greater than 1, which means this is a exponential growth problem. So if you know the y-intercept and if you know it's a growth, you know the graph should look like this. And let's check on Desmos. And as you can see, we were correct. It is exponential growth. Now, exponential decay. For this one, let's try y equals 2 parentheses 1/2 to the power of x. So let's graph it without a calculator. So let's start off with the y-intercept. So the a value is 2, so our y-intercept will be 2. So our graph will hit the y-axis at 2. Now, the b is 1/2. So the decay factor, or the factor is less than 1, so you know it's going to be decay. So if you read the graph from left to right, your graph should be going down. So something like this. Let's check on the calculator. So let me erase that one. So it was 2 1/2 to the power of x. And as you can see, it is an exponential decay, because if you look at the graph from left to right, it is going down. Now, one more important thing that you have to know about these new functions. Both of these functions have what's called a horizontal asymptote. So let's look at the graph real quick. So for exponential growth, notice that the graph goes flat right here. So I'm overlining it in blue. So this right here is what's called a horizontal asymptote. So a value that you approach, but you never touch. So again, it's right here. As you can see, it is going down. It is approaching 0. So you call that a horizontal asymptote at y equals 0. And again, the y equals 0 comes from the line that it approaches but never touches. So y equals 0. If we look at the problem on the right, the decay problem, if I look at the graph from left to right, it is decreasing and it is going flat, or in other words, it is approaching y equals 0. So again, the horizontal asymptote here, asymptote is also at y equals 0, because it approached 0, but it never touched 0. So let me show you guys the table for this problem so it can make more sense to you. So here was the exponential decay problem, and if I show you the table, here it is real quick. So let's look at the table and then let's look at the graph. So if I look at the graph starting from the left side, you can see that it is approaching infinity. So if you look at the y values, they're getting bigger. Now, if I keep on going, it'll be approaching infinity. But if you look at the y values going to the left, to the right, they are decreasing. So now if we look at the table, at x equals 0, the y value is 2. At x equals 1, the y value is 1. At x equals 2, the y value is 0.5. So if you increase the x values, it should be getting really, really small. So let's say x equals 10. That's the x value. Now let's say our x value is 20. So as you can see, you're approaching 0, because remember, times 10 to the negative 6, that means you're going to move this decimal to the left 6 times. So of course, that's really, really small. And let's try another x value, 30. So now the decimal is 9 units to the left. So of course, you're approaching 0, but you will never touch 0. So those are horizontal asymptotes. Now, let's identify if these three examples are exponential growth or exponential decay just by looking at the equation. So pause the video, try, then come back. So example number 1, the b is equal to 3. So the b is greater than 1. Therefore, this is exponential growth. Now, example number 2. The b value is equal to 5 over 3. And that b value is greater than 1. It is 1 point something, so it's greater than 1. Therefore, exponential growth. Now, example 3. The b value is 1/3. 1/3 is less than 1. Therefore, exponential decay. Now, given this function, we're going to identify the key features. So we're going to find the growth or decay factor, the growth or decay rate, the initial value, in other words, the y-intercept, the horizontal asymptote, and then the domain and the range. So let's start with identifying if it is growth or decay. So the b value is less than 1 because it's 3 over 4. That's 0.75. So therefore, this is an exponential decay problem. So let's find our decay factor. So our decay factor is basically the b. So again, the b is 3 over 4. Let's change it to a decimal to make the next step easier. So the decay factor, in other words, the b is 0.75. Now remember, the decay rate is the number that you have to subtract by 1 to get the decay factor. So if it is 1 minus the decay rate, that's what gives us 0.75. Now, just do a little bit of subtraction. What do you subtract from 1 to get 0.75? And that right there is 0.25. So our decay rate is 0.25. And this part will make more sense once we start looking at the real world problems. So that'll be on our next lesson. So the answer for part B is 0.25. And again, we got 0.25 because to get 0.75, you subtract 0.25 from 1. Now, the initial value or the y-intercept. The initial value or the a in this problem is 2. So the graph will cross the y-axis at 2. So right here. So let's write it as an order pair, 0, 2. So it is a exponential decay problem. So like this. And let's identify part D, which is the horizontal asymptote. So remember, it's wherever the graph goes flat. And of course, it is right here. And that y value is y equals 0. So HA at y equals 0. Now, the last part is domain and range. So the domain is from left to right, looking at the, so left to right, looking at the x value. So let's look at the graph real quick. So the graph goes this way to the left side, so it approaches negative infinity. As it goes to the right, it approaches positive infinity. So the domain is all real numbers. Now the range. Let me redraw the graph. It's getting kind of messy up there. So the range, remember the range is bottom to top looking at the y values. So the lowest the y value is right here. In other words, the HA. So the lowest y value is 0. Because remember, you approach 0, but you never touch 0. In other words, this graph will never be below the x-axis. So the lowest y value is 0. This goes up, approaching positive infinity. So in other words, everything greater than 0. So leaving our range to be y greater than 0. One more thing you should be asking yourself, do we include the 0 or no? So we mentioned earlier that for HAs, you approach them. So we get really, really close to 0, but we never actually touch 0. So therefore, the domain and the range are the following. Go ahead and try the following. Pause the video and then come back once you have your answers. So given y equals parenthesis 4 over 3 parenthesis to the power of x, identify the following. So first, let's identify if it is growth or decay. So the b value here is 4 over 3. 4 over 3 is, of course, bigger than 1. Therefore, it is a growth problem. So I'm going to cross decay out because it's not a decay. Now, let's find the growth factor. Remember, the growth factor is basically the b. So the b is equal to 4 divided by 3. Now, the growth rate. Remember, to get the growth rate, you have to make a little equation first. Let me erase this real quick. Now, for the growth rate, to get that rate, you have to do, since it is a growth, you have to do the following. 1 plus some number has to equal 4 over 3. Now, 4 over 3 as a decimal is 1.33333. So what do you add to 1 to get 1.33? And of course, that is 0.33333, which is, in other words, 1 divided by 3. So our growth rate is 1 over 3. And remember, this will make more sense in the next video, so I'll show you in a minute. Now, the initial value is the value of a. So if you look up here at the problem, I don't see a number right there. So if you never see a number there, know that it is a 1. So the a value is equal to 1. So that is our y-intercept. So 0, 1. So let's graph it so we can get the HA. So the y-intercept is 1. And earlier we said it was an exponential growth. So the graph should be increasing if we look at it from left to right. So here it is. So our graph goes flat again right here at the same value every single time. If you look at the graph from left to right, it is coming from really, really close to 0. It is going up, approaching infinity. So it went flat right here at y equals 0. So the HA for all of these graphs will be 0. It will change. It will only change if you have a shift up and down, so a transformation. We'll look at that in a minute. Now, the domain. So again, here's the graph. The y-intercept is 1. So the domain is from left to right, looking at the x values. So if I look at the graph from left to right, as this graph goes to the left, it is approaching negative infinity. As it goes to the right, it's approaching positive infinity. So the domain is all real numbers. So if you haven't figured it out yet, the domain for exponential growth and decay will always be all real numbers. Now the range. So remember, bottom to top, looking at the y values. Earlier we said that the lowest y value, or the HJ, is 0. Then the graph goes up, approaching positive infinity. So in other words, everything bigger than 0. And again, do not include the 0 because you have a HJ at 0, which means you never touch 0. And let me prove that to you using the graph. So let me go back and graph. Let's graph the one we just worked on. So 4 over 3 to the power of x. So as you can see, here's our exponential growth problem. And as I zoom in, notice that we never touch the x-intercept. So as you can see, it looks like it touches the x-intercept over here, right? So if I zoom in, I'm proving to you that we never touch the x-intercept. It will get really, really close, but as you can see, you'll never touch the x-intercept. So again, horizontal asymptotes you approach, but you never touch. Now go ahead and try the following problem, pause the video, and then come back once you've tried it. So given the following problem, identify the HA, the domain, and the range. Okay, so let's start with the graph. You know the y-intercept should be 1.3, so that's 1, that's 2, so 1.3 is about right here. The b value is greater than 1, so this is an exponential growth problem. In other words, if we look at the graph from left to right, it should be increasing. Now, part A is finding the HA. So again, the HA will always be 0 unless it has a... Okay, so here's why I gave you this problem. This problem has a transformation. So this problem is transform 2 units down. As you can see, we subtracted 2 at the end. So this is a transformation 2 units down. So let me show you how this affects your graph. Well, here, let me go back. So notice that we said that the HA will be at y equals 0 all the time. But if we move the graph 2 units down, if you subtract 2 from 0, your new HA will be at y equals -2. So let's graph it so you can see it. So it is 1.3, 2.5 to the power of x minus 2. Here, let me start over on this. So y equals 1.3. Okay, so here it is. We're on a better window. So let's see if we were correct. So initially our y-intercept was 1.3. Here, let me actually grab both before the transformation so you can see it. Okay, so that blue graph will be without the transformation. So our y value there was 1.3. But then remember, the graph was shifted 2 units down. So whenever you do 1.3 subtracted by 2, you get -0.7. So that's our new y-intercept on the red graph. And one more thing I want you guys to notice. So the HA, the part where the graph went flat, was 0. But since you move the graph 2 units down, the HA is now -2. So again, 2 things changed with that transformation, the y-intercept and the HA. So let's go back to our graph. So let me graph both for you. So without the transformation, here's the graph, but then we're going to shift that 2 units down. So remember, 2 things are going to change. The y-intercept is now at -0.7, so that's right here. And your HA is going to go from 0. Let me do that in green. It's going to go from 0 down here to -2. So your new graph is this right here in gray. So the HA, the part that the graph went flat, is right here at -2. So let's find the domain and the range for part B. So the domain is from left to right, looking at the x values. And again, we're only looking at the blue graph. So we're only looking at the gray graph, ignore the blue graph. So the domain left to right. As this graph goes to the left, it's approaching -infinity. As it goes to the right, it's approaching +infinity. So the domain is all real numbers. The range, bottom to top, looking at y values. The lowest y value is here at the HA, which is -2. Then the graph goes up, approaching +infinity. So the range is everything greater than -2. And of course, no equal to, because the graph approaches, it is increasing from -2 and it will never touch -2. So that was the introduction to exponential growth in decay.